I'm your host, Amir Jafari, and this is the third lecture in a series of lectures on quantum field theory. In the last two lectures, we briefly discussed the main ideas behind quantum field theory, the formulation of basically combination of special relativity and quantum mechanics, at least from the point of view of particle physics. Basically, what we had before, let me briefly mention what we had before, and then we can basically finish this introduction part of this course, and then starting from the next lecture, which is going to be this, the fourth lecture, we're going to start our formal development of the theory of quantum fields. We defined, I mean, it's hard to give a definition to quantum field theory because it's used in many different fields in physics, but at least historically or from particle physics point of view, you can say that QFT, quantum field theory, is the most successful theory we have for the combination of special relativity and quantum mechanics. Okay, what we had before, let me briefly go over this and then finish what we had previously. Let's start with quantum mechanics. We said that, and we try to combine quantum mechanics with special relativity. So let's discuss, what we know from wave mechanics, from quantum mechanics, ordinary non-relativistic quantum mechanics, very briefly. Well, we have this relation, the energy relation, for a wave function, and we define wave function as a probability amplitude. I'm not going to go through postulates of quantum mechanics. Supposedly you are familiar with them. But the idea is that you can say something like this. For Newton, in classical mechanics, x position, p momentum, e energy were just, well, Newton didn't work with energy as we do, but you get it, it's just classical mechanics. These variables, position, momentum, energy, in classical physics are just variables. They are scalars, vectors, etc. They're not operators. But in order to describe subatomic particles, quantum world, it seems necessary to promote these variables to operators. So we promote these quantities to operators. For example, in wave mechanics, where you work with a wave function like psi, which is a function of space and time. P is in position representation, one representation, because I'm assuming that you are familiar with non-relativistic quantum mechanics, so I'm just sketching out some important details. Minus I h bar, Planck's constant, gradient operator, and energy would go something like this, time derivative, etc. So this is called, and you say that, well, x and p in one dimension, you can generalize this to 3 dimensions, satisfy this kind of computation relation. So you're promoting these variables to operators and also impose some commutation relation like this, and this is called the first quantization. Well, this is basically a misnomer because we're going to talk about second quantization in a moment, and that's the reason why I'm mentioning this. But you can remember this, or you can understand this, although not very appropriate naming, that because this is quantum mechanics, we call it first quantization. When we go to quantum field theory, we're going to have second quantization. Okay, so we can put it this way. Okay, so this way, what do you get? You say that in, again, classical mechanics, the Hamiltonian for a single particle with in some potential is something like this. Now, position and momentum and energy are promoted to operators, so Hamiltonian is an operator. Then if you write this equation that I wrote before, actually, and this is IH d psi dt, what you get is the Schrödinger's equation. Okay, but look at what we do here. We say that, I mean, there is no problem with these two. I'm not discussing these two, but look at this. We basically impose this, operation. We basically say that position is promoted to an operator. But time is time. No one touches time, right? This makes sense in non-relativistic quantum mechanics, and here we discuss it, the non-relativistic theory of quantum mechanics. In other words, it's okay if we treat space and time not on same footing, asymmetrically, in other words, okay? But then when we try to get this generalized to relativistic realm in getting, special relativity into play, we did something like this. We said, well, instead of this Hamiltonian, which is a classical relation for the energy, use this relation, which is the familiar energy relation in special relativity. P is momentum against c speed of light for a particle of mass m, right? And we call this Hamiltonian because P is a momentum from here, an operator, momentum operator. So we write this energy relation in this form. So this is now minus, here we get minus h squared, basically t squared psi from this relationship. And instead of this p, we have here this operator, again, the same, kind of a second quantization, and you get this Klein-Gordon equation. And the Klein-Gordon equation can be written as, I don't remember last time what kind of notation I used, but you can write it as this equation, minus m squared c squared hy squared psi. And this is the Klein-Gordon equation. And we hoped that this equation would be the generalization of the Schrodinger's equation to relativistic quantum mechanics. Okay, this is going to be relativistic Schrodinger's equation, if you like. But it didn't work. We learned that if we are going to interpret psi as a wave function, that's to say that we interpret psi as a probability amplitude, then we're going to get to in the problem of or trouble of negative probabilities. So this doesn't work for psi interpreted as a wave function. Okay, this doesn't work. And we said that because of this reason, well, we discard Klein-Gordon equation. Maybe. All right. That's the Klein-Gordon equation, and that's what we have. Then we discussed Dirac. Dirac tried to basically linearize this Hamiltonian and got to the famous Dirac equation, but it has similar problems. It gives us negative energies or no ground states and problems like that. Okay, so what we have, the Klein-Gordon equation. The Dirac equation is kind of similar. This equation for spinless particles in principle, because we don't try to incorporate spin to this formalism. But the Dirac equation has already the spin-off particle in it. So I'm not going to discuss the Dirac equation because mathematically it's complicated. But the same arguments can be applied to the Dirac equation as well. So what we have is basically the Klein-Gordon equation. In our attempt to combine special relativity and quantum mechanics, now we have this problem that this equation doesn't work. It gives us negative probabilities. What to do? Discard this equation altogether? Well, maybe. However, we should mention something else. I should mention this because we talked about this formalism here. In the first quantization here, we say that, well, x position, momentum, energy, these go to operators. We promote these to operators, and we impose, commutation relations like this between x and p, for example. But as I mentioned a moment ago, here you see that we promote x apparently to an operator, but we don't touch time. And I said that it was okay for the Schrodinger's equation because in that context we have no relativity. It's just, Galilean transformations or in non-relativistic setting. But here we are trying to combine special relativity with quantum mechanics. So you have to worry about this behavior. We are treating space and time separately, differently, basically, and not on the same footing, asymmetrically. And this is not, this is against the spirit of special relativity. We shouldn't do this. In getting the Klein-Gordon equation, this equation, we should worry about doing something like this. This first quantization about position. Okay, so something seems to be wrong from the outset. We did something, maybe wrong, not reasonable. Okay, and then we said that, well, it doesn't work because it gives us negative probabilities, and we discussed that physically. It's related to this fact that, well, you are trying to write a differential equation for a mass m, and you interpret this as a wave function, right? Obviously, it's not going to work because this wave function, within principle, supposedly, describes a just one particle, or a fixed number of particles. But we know from special relativity that E equals mc squared. Now, in a relativistic setting, we know that you are working with high energy particles moving fast near the speed of light. So you're going to have, enough kinetic energy to create new particles. So you might begin with one particle, okay, in, say, an experiment, but because of high energies involved, it's possible, due to this equation, famous equation in physics, new particles are going to pop out and you have no formalism to describe them or predict them. So that's the reason that this equation doesn't work and you might drop it. Okay, so we discussed this and you remember all this discussion. Now, where's my pen now? This was, no. I kind of, oh, okay, here. So, now, we say that, okay, probably, perhaps, psi, the solution of this equation, shouldn't be interpreted as a wave function. What about this? So, we know that the Klein-Gordon equation doesn't work for a wave function. If you are going to interpret the solution as a wave function, it doesn't work. E equals mc squared, new particles pop out, okay, we know this, so it doesn't work. Now the idea is that perhaps psi solution is not a wave function. Perhaps this equation describes something else, and we are misinterpreting this equation, the solution of this equation. But the mathematical form of the equation might be the correct form. Because, yes, there was this problem about, first quantization. We are treating x and time, position, space and time, a different footing. But we didn't use that directly in this derivation. We just did use the fact that energy is an operator like this and momentum is an operator like this, but we didn't use this, okay, at least directly. And, well, this is a special relativistic equation, reasonable, and also these operators, P and momentum and energy, are, reasonable operators in ordinary quantum mechanics. So we didn't use anything like incorrect, or unreasonable, either from special relativity or quantum mechanics. So the idea is that the mathematical form of this equation might be, the right one, but what's wrong is our interpretation of the solution. The solution is not a wave function. It might be something else. So what is this solution? Well, we have this derivative with respect to space x in 3 dimensions, Laplacian, second derivative, and we have this derivative with respect to time, space and time treated on the same footing, good. Special relativistically, we are good. And psi is not a wave function. We are assuming that it's not a wave function, so there is no problem of negative probabilities. So we are looking for some physical interpretation. What's psi? Well, from here we know that psi is a function of x and t, right? Because we have derivatives with respect to x and t. So perhaps this is a differential equation for a field. What is a field? I mean, classically, in classical physics, a field is a multivariable function for mathematicians, but it gives you some quantity, something, a scalar, a vector, a tensor, we discussed this before, at any point in space and time. And here you go, this is a function of space and time. It gives you something, we don't know what yet, but it gives you something, a scalar at any point in space and time. So it's a field. So this is a classical field. So far, I have no idea about the physical content of this equation, but I know that it's a classical field. It gives me something. The solution should tell me something about, some physics at any point in space and time. So it's a classical field. This is the definition of a field. Like, for example, temperature field. In a room with temperature gradient, you have different temperatures at different points. So temperature at any point gives you a scalar, which is temperature at that point, right? Temperature field. Or concentration field. You drop a drop of ink in a glass of water. At any point, you have different concentration fields. Concentration of ink, it's a scalar field. You have vector fields, magnetic fields, electric fields. So we are familiar with this notion of field, and here we go. We have a field. And in fact, we have familiar equations from classical electromagnetism, which is exactly this equation. Remember, if you write down the Maxwell's equations in vacuum, there's no current, no charge density. What you get for vector potential, remember, vector potential is defined this way. A is the vector potential, B magnetic field. This is the definition of vector potential. If you write down Maxwell's equations, which is dt, this is curl of B dB dt curl of E minus plus, and divergences would vanish, okay, in vacuum. So from here, it's easy to get this equation. The second derivative with respect to time minus A equals 0. Exactly the same equation. Well, not exactly. On the right-hand side, I get 0 for the vector potential. The vector potential gives you electric and magnetic fields. Remember, electric field is also as minus dEA dt minus A0. What's A0? A0 is what we usually call phi, scalar potential. But because I'm going to use phi for the solution of the Klein-Gordon equation, or I might have used it before, so I'm just using A0. And in a relativistic setting, a mu, the 4-vector potential, is defined something like this. Okay, so A0 is scalar potential. So, long story short, this is the familiar equation for vector potential in vacuum in classical electromagnetism. No one interprets A, the vector potential, as a wave function. This is a field. This is a vector field. This is a classical vector field. Okay. And as I said, you might say that no, this is not exactly the same equation mathematically. On the right-hand side, you have 0. But perhaps, notice, here, what we have, this equation, the Klein-Gordon equation, has this m, mass of particle. This is the mass of particle, and this is 2, by the way. Okay. So if you interpret it, again, I'm repeating myself many times, but these are important. If you are going to interpret psi, the solution of the Klein-Gordon equation, as a wave function, then this approach is doomed. Why? Because you are putting the mass of the particle m there, but you're going to create, different particles in the relativistic setting. Okay, so it doesn't work. But now, what's the meaning of m there? Perhaps this field, this solution psi, would create a particle of mass m for us. We were looking for quantum fields, remember? We said that because this Klein-Gordon equation in this form for wave functions fails, this approach fails, we need a mathematical formalism, a mathematical object, if you like, which is a field, because we need to create and annihilate particles at any point in space. And at the same time, it has to be an operator, because you are working in the context of quantum mechanics. If you have one particle at any moment of time, you are in one particle state, quantum mechanically. When you apply this field and create another particle, if you're successfully, develop this theory, at the end you're going to have this formalism. You operate with this field on quantum states to jump from one particle state to two particle states. So when you create a particle, in other words, you are jumping from one quantum state to another quantum state. One particle state, by creation of a particle, you are jumping to two particle states, so on and so forth. Okay, so what you need is a field which is at the same time an operator. Okay, now we got the field part. Perhaps what we are looking for is the solution of the Klein-Gordon equation, but it's a classical field. It's not an operator yet. Okay, but we are hoping that we are getting there. We are hoping that this psi is going to give us quantum field, a quantum field which creates this mass m. So there is no problem by writing this mass, by putting the mass of the particle in this equation, because we are not interpreting the solution as a wave function. We are interpreting the solution as an operator and a field. It's going to create a particle with mass m. The mass of particle is here, no problem there. So if this is the way to go, then you can say that, well, look at here. A vector potential, this equation over here, can be written in this form. What is MPH? M, mass of photon. Because we know that radiation field, electromagnetic field, is related to the concept of photon. Einstein told us about this in 1905, remember? You can imagine a radiation field, electromagnetic field basically, Maxwell's field. And Einstein told us, well, look, quantum mechanically, this is just a bunch of particles, a rain of photons, if you like, okay? But mass of photon is zero. So this, oh, I'm sorry, this is, this is A. Mass of photon is zero, so the right-hand side of this equation is zero, and we're good. This equation, the Klein-Gordon equation, is exactly the right equation for the vector potential. And vector potential is not a wave function. We interpret it as a classical field. That field gives us what? The magnetic field, the curl of that, and electric field. I wrote down these equations here, but one more time. Phi, the scalar potential, if there's no confusion about the notation. Okay, so we see that we are getting there. The Klein-Gordon equation should be interpreted as the differential equation for a field, but a classical field. Exactly like the partial differential equation for vector potential for radiation field. Now, if we quantize radiation field, if we quantize the magnetic field, we're going to get photons. We can create and annihilate photons. The number of photons in any system is not fixed. You know that. Okay, from statistical physics, for example, when you get Bose-Einstein, statistics, if you remember. Otherwise, you can refer to any book on the statistical mechanics to refresh your mind. But the number of photons in any system is not fixed. Photons come and go. They are created and annihilated. So if we quantize this classical field, vector potential A, we are going from classical electrodynamics or electromagnetism to quantum electrodynamics. So The next step is to quantize these fields, to quantize this Klein-Gordon field and quantize radiation field A. But we have no idea how to do that yet. Okay, just bear with me. So what we know now is that, well, if you treat the Klein-Gordon equation as a partial differential equation for a classical field, it resembles the differential equation for a vector field in electromagnetism, the vector potential A. Okay, and the similarity is very good. I mean, it's very suggestive. So we are getting somewhere. We got the classical field part. We got the field part. Now we are going to make this field a quantum field. Okay, how? We'll see in a moment. Let me write these equations one more time because I have little space here. The Klein-Gordon equation, one more time, is this equation. So by the way, I'm going to be sloppy about units. Sometimes I write speed of light c, h bar, Planck's constant. Sometimes I'm going to forget because sometimes I can get lazy, or on purpose, because in real calculations in quantum field theory, no one writes these constants because almost everyone works in natural units. So c, speed of light, and h bar, Planck's constant, are equal to unity in those units. So I'm going to forget sometimes. I'm not going to forget sometimes. This is on purpose sometimes, again, because I want you practice. If you see any equation where there is no h bar, no c, do dimensional analysis and recover h bar and c and other constants like them. So move from natural units to whatever units you want. Okay, this is the Klein-Gordon equation. And from Maxwell's equations in vacuum, you got, well, it's not symmetric now. I have to write Maxwell here. Ta plus n a equals 0. And we know that the right-hand side, I might have a non-zero term, but because the mass of photon empirically is 0, so the similarity is good. Okay. Right. So we have an equation for a field. A is a vector field, and psi is a scalar field. If you remember last time, in the last lecture, we talked about this idea. I'm repeating again because these are important. Once you have a field, you can imagine that any excitation in this field would give rise to particles. But this is very rough. This is extremely plain language. What do you mean by disturbing a field and creating a particle? I mean, it sounds nice when you are just having a beer and talking about that. But I mean, mathematically, what do you mean? Now, in this lecture, we are going to make this precise and finish our introduction. And then we're going to have the big picture of what we are trying to do in quantum field theory. And the rest of the course will be just details, in some sense, okay? But I'm oversimplifying things here, but bear with me. It's going to work, I promise. Okay, we have these equations similar, and we're trying to quantize them. We're going to interpret them as classical fields for now. Classical fields, both of them. Now the question is how we can make them quantum fields. Okay, how to make psi and a quantum field. We can do it just for the Klein-Gordon equation, and you're going to see that it works reasonably well for Maxwell's fields as well. If we quantize a vector potential, we're going to get photons. We're going to get an operator called A with a hat, a quantum version of A, which creates and annihilates photons. Photon is the field, corresponding to this equation here, Maxwell's equation, classically. And here we're going to get a quantum field, quantum scalar field, psi with a hat, because now we're making it an operator. We'll see how. which creates and annihilates particles with mass m and no spin. Massive spinless particle, the Klein-Gordon particle, if you like. How to do that? Okay, we need some physical intuition here, physical, maybe a thought experiment or something like that. Okay, what example? I gave you an example previously. If you remember, I talked about this swimming pool, right? Imagine that you have a swimming pool, and well, this is a two-dimensional manifold, basically, the surface of water. So you can imagine why any point on the surface of water, you can define a depth of water. Okay, now this x, vector x, is basically x and y, right? Two-dimensional example, but it doesn't matter. It's a field. This is a classical field as well. Like psi here and A, it's a classical field because it gives you something, a number, right, at any point in your manifold in your system space. If you have a wave, for example, on the surface of water, h would change periodically in the sine and cosine functions. You are familiar with this periodic. I mean, in practice, it's going to be complicated because you have two dimensions, etc. But you know what I mean. It's a wave, and it can be described in principle by this field H, variations in this H, and it's a classical field. Now, if you want to, and also speaking metaphorically, at least just kind of, swimming pool, from quantum mechanics, you know that if you have a wave, you can, it can represent a particle. Particles and waves are kind of corresponding in wave mechanics, in quantum mechanics. So if you have a wave, you can describe it by this classical field, and quantum mechanically, you know that it can represent a particle, right? Now, in quantum field theory, you want to create and annihilate fields, create and annihilate waves or particles. How we do this in a swimming pool? Well, as I said before, you drop a pebble and you excite this field H at that point where, pebble touches the surface of water. And this excitation gives you some waves, okay? And waves quantum mechanically represent particles. So you have created a particle, or two particles, maybe three particles. We'll talk about this. Okay, so what you do here is spend energy by dropping a pebble. You can spend more energy by dropping pebble forcefully or less energy. It depends on you. You spend some energy. That energy excites the field. The depth of water changes depth of water. It creates a wave. That's it in a swimming pool. But if you are talking metaphorically, and you know quantum mechanics, you know that waves, after the first quantization, can represent particles. I mean, quantum mechanically, waves and particles are kind of related. So if we can formulate this in the same way, we can apply this idea to the Klein-Gordon equation. We have a field here as well. We can excite it by spending some energy, by using some energy at some point in space, and that excitation in psi is going to give us particles. But how? Again, this is classical physics. We don't know how to move to quantum mechanics. We don't know how to quantize these classical fields. This is a classical field. This is a classical field. Depth of water is a classical field. Spending energy, excitation in these fields creates waves, but we don't know how to get from waves to particles. This is going to be our next task. But in order to get there, get the idea of how to do this, still classically, look at this point. What happens here? Again, I've mentioned this previously, but just to make you remember and think about this, you get some oscillation. Classically, you get some oscillation there. So when you say oscillation to a physicist, the first thing they might think of is a simple harmonic oscillator. It's the simplest system, physical system, where you can study oscillations, vibrations, periodic motion. So perhaps we should put a simple harmonic oscillator, a spring here with some mass in it, okay? And we can formulate mathematically what we are trying to do in this way. We say that oscillation on the surface of water is like, giving energy to a simple harmonic oscillator, okay? Classically, we're done. Okay, so what? If you are doing this in the realm of classical physics, I mean, nothing is going to work. But we know that if this is a simple harmonic oscillator, we know how to treat simple harmonic oscillator in quantum mechanics. Okay, how? We write down Schrödinger's equation for that. We get the energy states. Energy states are discrete, etc. You're familiar with that, and I'm going to review it for you in another formalism. But the idea is that if you do this, if you imagine that oscillation on the surface of water in this field, depth of water, acts like a simple harmonic oscillator there, then it's easy to move to quantum mechanics. Because if you imagine that simple harmonic oscillator is a quantum simple harmonic oscillator, you know that the energy of a simple harmonic oscillator is given by this expression. N is a positive integer, 0, 1, 2, etc. H bar Planck's constant. Omega is the angular frequency, which is basically classically K over M. Spring's constant over mass. Okay, for us here, omega is a constant, system's constant. Okay, so you drop a pebble, not forcefully. You spend not much energy. You get the simple harmonic oscillator gets excited to its first state, n equals 1. If you do nothing actually before that, let's say this. If you don't drop any pebble, if you do not create any particle, right, it's in the ground state. The simple harmonic oscillator is in its ground state. When you drop a pebble, very weakly, just barely touch the surface of water, you get to the first excited level of simple harmonic oscillator at that point where the pebble touches the surface of water. If you do it a little bit forcefully, you get the second excited level for that simple harmonic oscillator at that point. If you do it more forcefully, you're going to get to E3, 4, etc. Now, the idea is that these energy states can be interpreted as having a number of particles. Here you have 0 particles. You haven't dropped a pebble. You haven't disturbed water. This field, depth of water, your classical field here, is not touched, is not excited. So you have 0 particles. You are in a vacuum state. Vacuum state means that you have a swimming pool, there is no wave, no particles. Now you drop the pebble, and just a little, disturbance, you create just 1 particle there, because that simple harmonic oscillator gets to the first excited level. If you spend a little more energy, you're going to create 2 particles. So you see, different excited levels of the simple harmonic oscillator can be interpreted as representing different particles. You can create more and more particles by spending more and more energy at that point. So if you want to create any number of particles in the swimming pool, put simple harmonic oscillator here, simple harmonic oscillator here, simple harmonic oscillator here. At every single point in space, you put a simple harmonic oscillator. When you drop a pebble there, this is how it works, n plus 1/2. For example, you drop pebble here, you're gonna get, if there is no pebble, no excitation, you get either just the ground state, vacuum, no wave, no particle. If you spend little energy, you're gonna get one particle, h omega plus h omega. And as I said before, you can create more and more particles. So different excited levels of simple harmonic oscillator represent particles there. So you can create any number of particles at that point that you want by exciting that simple harmonic oscillator. So the idea is to imagine that at any point you have the simple harmonic oscillator, but that idea requires that you put simple harmonic oscillator inside these equations, right? How we do this, again, I mean, using simple words in plain language like this and using some graphics, etc., well, looks fine, but how you do it, I mean, mathematically? Well, it's actually easy. In fact, if you look at these equations, the Klein-Gordon equation and this equation from Maxwell's equation for the vector potential, you can see the simple harmonic oscillator inside them. You say no, just look at here. Again, because of space, I have to write this Klein-Gordon equation one more time, and I'm going to keep for now, well, no, now I have to drop writing speed of light and Planck's constant. I'm going to call this quantity mu squared, okay, for simplicity, because it's a constant related to the mass of particle. Okay. Now, as a mathematician, just as a mathematician, imagine that you are not a physicist, you don't know any physics behind this equation. And we don't know, we are looking for an interpretation, right? We know that psi is a field, a classical field, it's not a wave function, but we don't know what exactly it is. Okay, what a pure mathematician, how a pure mathematician solves this equation? Well, one way is to write down a Fourier transform, right? Let's use this notation. For example, A P T E P X plus, because in principle and in general, this field psi can be a complex function, so I write down this Fourier transform in this form, and you see that I'm dropping h bar here. I mean, dimensionally, you can put it there and interpret p, but not important for us now. Just mathematical, a Fourier transform. That's it. And I'm dropping also constants like this in the definition of Fourier transform. Again, this should be fine. Now, if you do this, what do you get for the second derivative? Well, the second derivative with respect to time would be, because just A and complex conjugate of A depend on time, so you're going to get IPX, and by double dot I mean the second derivative with respect to time, because it's a function of P and P, the dummy integration variable, and or Fourier mode, or whatever you call it, and time is time, PTE minus IPX. It's very elementary, but I don't know why I'm writing this, but still, I'm writing it for being extra clear. A P T E minus IPX P, because if you apply Laplacian to exponential functions, it's time, derivative with respect to position twice, the second derivative. So you're going to get IP minus P squared here. So if you put these, plug in back to the Klein-Gordon equation, here, what you get for these would be something like this. Let me change my color. A minus mu square plus p square a. Or you can call this omega square p. And also for the complex conjugate, you're going to get this equation for that. What is this? The differential equation for a simple harmonic oscillator. This is familiar, right? Even if you know just Newton's second law, you can get this. F equals ma for a simple harmonic oscillator, mass, constant of the spring's constant k. This means m double x Hooke's law kx, and from here you get x double minus omega square x, and omega square is k over m. Right. Simple harmonic oscillator. So inside this equation, the Klein-Gordon equation, there is a simple harmonic oscillator. Okay, you can see this by Fourier transformation, right? So now here, what we have in simple harmonic oscillator is that you have a ground state E0, you may call it. The first excited level, H omega, again I'm repeating this one more time because it's extremely important you get an idea of. As you increase the energy, I mean classically, in classical physics, in Newtonian mechanics, if you have a simple harmonic oscillator like this, if you increase its energy, X is basically given by this kind of equation, right? In classical Newton. Plus I, well, let's write it this way. A Jafari minus. If you use complex solutions for this equation, you can write it this way. Okay. And what you get for the energy is a continuous function. I mean, energy of the simple harmonic oscillator in classical physics increases continuously. But when you approach simple harmonic oscillator quantum mechanically, you see that X becomes an operator, and the solution is given by this kind of function. Now, A and the dagger are operators like X. I'm gonna show you how you get this. But if you're familiar, and you should be actually, because this is just simple non-relativistic quantum mechanics. If you know how to solve the problem of simple harmonic oscillator in quantum mechanics, you are familiar with this notation. But I'm gonna get it for you. So from Newton to quantum mechanics, what you do is that X here for Newton is just position, a number or vector in 3 dimensions, and you write it as a complex form in general in this form. But in quantum mechanics, you see that X is an operator now in ordinary quantum mechanics, and it's given by this form, and A and the dagger now are called creation and annihilation operators. We're going to get there. But the most important thing here is that the energy goes this way, and you can interpret the nth excited level as having n particles. So as we excite simple harmonic oscillator and go up on this ladder of energy, it's like creating more and more particles. Okay, so that's the idea. Now, let's treat simple harmonic oscillator quantum mechanically, just to refresh your mind, and get back to see how this this transition happens actually, and how we can use this here in our main problem, how we quantize the Klein-Gordon field. Okay, so simple harmonic oscillator, simple harmonic oscillator in quantum mechanics, or you can call it quantum simple harmonic oscillator. Okay. So, because again, this can be found in any elementary book on quantum mechanics, ordinary quantum mechanics. So I'm going to be kind of quick. So let's just start with Hamiltonian. You write down the Hamiltonian as p squared over 2m, p momentum, obviously, m squared x squared. Now we have this simple harmonic oscillator, m, k, omega is angular frequency. Now we are trying to solve this in quantum mechanics. This is the Hamiltonian. Hamiltonian is an operator because p and x are operators. Remember, x is promoted to an operator. P is promoted to an operator. Energy is promoted to an operator. The first quantization. Quantization. Okay, remember this. And so now you can write down the Schrödinger's equation, which is basically this equation, right? Solve it, and you get psi, and from there you're going to get this relationship for energy, right? And this is basically what we need, but we need one more thing. I mean, you can get this easily by writing down and solving the Schrödinger's equation, but that method, Schrödinger's equation, is kind of lengthy, and not very, suggestive here. There's another method, also found in any textbook on elementary quantum mechanics, from Dirac, which is very useful here. And that is going to give us this solution. What is that? Well, you can write x, which is an operator, and also p, which is an operator in this Hamiltonian, in terms of these two operators, which are called creation and annihilation operators for obvious reasons to be discussed very shortly. And also this means that you can write A in terms of x and p, and a dagger in terms of x and p. And when I do this, write something like this, I mean that there are coefficients, etc. For example, to be extra clear, A is defined as square root of m omega over 2 x plus, I guess, ip over m omega. I mean, this is just convention to get simple equations. And a dagger is defined as a complex conjugate of this minus ip over m omega. And because x and p now satisfy this commutation relation by definition, first quantization, remember. So from there you get this relationship, this commutation relation for these two operators. Okay, again, you'll see that I'm dropping h bar here, Planck's constant. So you can recover it, for example, here. Okay, but it's not important. Right, and then you'll see that easily, it's really easy to get this. Hamiltonian, this Hamiltonian over here, can be written in terms of these operators, which is now very easy to write, plus 1/2. And it's also useful to define number density as a dagger A. So this is usually written in terms of n plus 1/2. You see that I'm keeping h bar here because this form is very familiar. I mean, h bar, omega, and for energy relations. So I'm keeping h bar in some place and then dropping it in other places. So this is Hamiltonian and the number operator. The important thing here is that if you write down the eigenvalue problem for energy, let's use this notation, n in bracket notation, the Dirac bracket notation. Let's call the energy eigenstate like n, And then from here, you'll see that, as I said before, En is given by n plus 1/2, n is 0, 1, 2, etc. And when a dagger applies in the same state, energy eigenstate, it gives you n plus 1. And when A applies on energy eigenstate n, it gives you. And notice that this means that by operating creation operator, you are jumping from energy state En to, which corresponds to this eigenstate, to energy corresponding to this eigenstate, En plus 1, which is basically En plus h omega. And by applying A on this energy eigenstate, you're basically jumping from En to En minus 1, which is En minus h omega. In other words, these are creation and annihilation operators. They create or annihilate one quantum, okay, with energy h omega. So this is why we are calling them creation and annihilation operators. And this is why basically we can use this formalism to create and annihilate particles in our problem of swimming pool. We said that put simple harmonic oscillator here, here, here. When you drop a pebble, spend energy, that spring, that simple harmonic oscillator is going to get excited. And that excitation means that as you excite more and more, as you spend more and more energy, you are creating quanta, particles, each with energy h omega. So you are creating more and more particles. And if there is no disturbance, if you don't touch the surface of water, if you don't touch your field, it's just vacuum. And energy is just the ground state energy, h omega over 2. And by the way, as again, to remind you, this A and the dagger are like operators, obviously. So they should satisfy the Heisenberg's equation for the system, which gives you AT E minus I omega T A 0. This is a time evolution of these operators, okay? So, in simple harmonic oscillator, long story short, you start with Hamiltonian given here, right? And you write down x in terms of these new operators, p also in a similar fashion, right? And say that x and p, first quantization, satisfy this commutation relation, and from there you get this commutation relation, okay? And now, from Newton, that we had x a I omega t, a minus I omega t. Remember, this is just sine and cosine function. In classical mechanics, simple harmonic oscillator has solutions of sine and cosine, and the general form of that can be written this way. Okay, so xt classically can be written in terms of a and a complex conjugate of a, which is just a number, a complex number, and also e exponential of I omega t and minus I omega t, just sine and cosine functions, just the general solution. And now you see that from Newton to quantum mechanics, what basically you do is that you get this a, because we write these as, remember, we write x and p in terms of these new operators. So basically you write a x position in terms of these operators. And we said that, well, at, time dependence, is this way, or you can put plus here, and a dagger t would be minus sine omega t, just to be consistent. For the complex conjugate, you get a similar relation. So from here, you're going to get a 0e plus a dagger e minus sine omega t. So this is xt. So in quantum mechanics, you get this. In classical mechanics, get this. What's the point? The point is that when you do the first quantization, you're promoting x to x hat, an operator, and look what happens. You are just writing this form in terms of new operators for the position x, okay? And also you get these energies, so you can interpret the excitation levels as, having different particles, and A and A dagger are acting like creation and annihilation operators. Now you say that, well, let's get back. Get back to our Klein-Gordon equation. In the Klein-Gordon equation, we wrote this solution. Now we don't need this here. We wrote it this way. Now compare it to this. E minus omega t, something like this. I don't remember. What kind of notation I use this. Look at this. In non-relativistic quantum mechanics, we treated simple harmonic oscillator in the quantum mechanically, and we got this solution in terms of creation and annihilation operators. Now here, for the Klein-Gordon equation, the classical field, the classical solution, we have this form. This is just a Fourier transform, right? We said that, well, when you promote x to an operator, you are doing something not very reasonable. I mean, there's something wrong according to special relativity, because x, if you are promoting x to an operator, you should promote time to an operator as well. And there are theories, quantum field theories, which basically do this, but we're not going to talk about them. Because we don't want to touch time, we're not going to treat time as an operator. So we shouldn't treat x position space as an operator as well. So you say that, well, what to do? We say that, well, x is not an operator. Instead, x is a label, like classical physics, but psi, this psi is an operator. I had some technical difficulties here, sorry. Okay, so the idea is that you write down this Klein-Gordon equation. I'm writing it for the last time in this lecture. E square phi minus del phi minus mu square phi. This is similar to, if it helps you to remember how we proceeded. For example, this equation for the vector potential, no one interprets A as a wave function, so we shouldn't treat phi, the solution of the Klein-Gordon equation, as a wave function. Instead, it's a classical field. And we say that this is similar to depth of water, the field, which gives you the depth of water in a swimming pool. How you create waves in the swimming pool by spending energy and creating, exciting this field. Similarly, you can excite A or excite phi in these equations, in these systems, to create particles. Of course, the excitation of this classical field would correspond to just vibrations, just oscillations, but you can quantize those oscillations in the same manner that we quantize simple harmonic oscillator in ordinary quantum mechanics. And then we can define a quantum field corresponding to the Klein-Gordon equation as A P P. Now A is an operator, E I P X plus a dagger E minus X, and we saw that the same thing can apply to A xt, and we're going to do this. We're going to quantize. This is the second quantization. When you have a classical field, phi or a, and you promote it to an operator, it's called the second quantization. So here we do not touch space. We do not promote x to an operator, unlike ordinary quantum mechanics, just the field itself. So, and from our previous discussion, now we see that A and the dagger satisfy the equation for simple harmonic oscillator. So you can write this also as, let's put it this way, AP, but at time 0, the time dependence can be written as this way. So you write it this manner, P at time 0, A plus I omega t minus I px 3p, which is similar, if you remember, to writing down x in ordinary quantum mechanics and as an operator. But here, again, to repeat, because it's important, we're not going to treat x as an operator. It's just a label. We use the similarity in order to, define our quantum field. Okay, so what this, by the way, if you look at this expression here, okay, here, you can write it in a relativistic notation as minus I p mu x mu, and this is going to be I plus I p mu x mu in terms of form momentum and space-time actually notation in this way. Okay, so this is basically a definition of a quantum field, and this is our result for now. This is our physical result. This is the way to proceed by defining a quantum field for the Klein-Gordon equation in this manner, and then see what happens. We're going to see that what we get is something like this. Phi x now is an operator. It's not a classical field, right? This is written in terms of, basically, you can write this equation as something like this. A plus a dagger p p. Okay, just to give you some hint of what's going on here. We're going to discuss this in detail later. But when you apply phi x to the vacuum state of your theory, when there is no particles around, that state can be written in this way. You can define the vacuum state this way. It's going to give you a particle at point x. Okay, this is our definition. This is how we will proceed. And now you see that phi x as an operator, as a quantum field, as a field operator, is written also in terms of these operators in momentum space. And in momentum space, if you apply this to the vacuum state, in that representation, it's going to give you a particle with momentum p. And annihilation operators, go the same way, reverse manner, if you like. Again, we're going to discuss details, but this is how you get this picture of exciting a field and creating a particle. So, exactly like that example of swimming pool, in space, in real space, in three-dimensional space, you imagine that your space is filled with this field. Okay, everywhere you have this field. And when you want to create a particle, you basically spend some energy, you excite this field phi, and that excitation gives you a particle at that position. Or in momentum representation, you can use these operators in Fourier transformation to create a particle with momentum p, or annihilate a particle. Of course, we're going to have commutation relations, for example, like phi x and phi y. What is this? Or AP and a Q, different momentum. What is this? We're going to impose these commutation relations. So when we say second quantization, it means that you are making this phi classical field an operator with some commutation relations. It's called second quantization, exactly like when you say X and P in ordinary quantum mechanics are promoted to operators, you have to impose also a commutation relation like this, or with H bar like this. So promotion to operators with some commutation relations. Here, promotion to an operator for the Klein-Gordon field with some commutation relations. We'll discuss these details of these relations and why we have them. We're going to get to different statistics like Bose-Einstein or bosons and fermions, etc. So I'm not writing details here, but the idea is to define a quantum field in this manner, and then you easily see that by exciting the field, you are basically exciting a simple harmonic oscillator at any point that you want to create a particle. Now you spend more energy, you get to higher excited levels of simple harmonic oscillator, and the crucial relation is this relationship for simple harmonic oscillator. Spend more energy, you can excite this to higher excited levels and create more particles. That's it for now. In the next lecture, we're going to start with this definition basically for a quantum field, and we're going to apply it to the radiation field, and you're going to see that from there we get the picture of the radiation field, electromagnetic field in terms of photons. So you are already familiar from, for example, your exposure to elementary courses in modern physics, that energy of a photon, according to Einstein theory, is given by, well, basically you can write it, E of one photon is h omega. Energy of n photons, if the density of photons in the volume is n, is this one. And you see that this is related to simple harmonic oscillators. So you see this picture of photons, and simple harmonic oscillator kind of deeply related. Excitation in a simple harmonic oscillator can be interpreted as having particles, each particle with momentum h omega. You can create and annihilate photons. You can create and annihilate Klein-Gordon fields. Each particle has h omega energy. As you spend more energy, you create more and more particles, more and more quanta. This is the big picture. I guess we're done with this, elementary treatment of quantum field theory. You should have some, rough picture of what's going on, why we are treating quantum fields or defining quantum fields this manner. But otherwise, you have to basically think about this. Think about the similarity between simple harmonic oscillator and Klein-Gordon equation. Write down these equations, write down these expressions for energy, for, all whatever we had here, these creation and annihilation operators, and think about them. You're going to get some similarity between quantum simple harmonic oscillator and these classical fields, the Klein-Gordon field and radiation field. And then remember that what we have here as a quantum field is just a definition. So I should emphasize that this is a definition motivated by our treatment of simple harmonic oscillator. But when you do this, you're going to see that the rest works out very well. You can create and annihilate particles, you get different statistics nicely, and the whole formalism works very well. So I guess at this point we're done, and in the next lecture I'm gonna quantize the radiation field, and from there you'll see that the energy, this is the last expression that I have for this lecture. Let's wrap up here. The energy of electromagnetic field, energy density, is given by this expression, if you remember from classical electromagnetism. if you quantize A, you're gonna get U something like this, H omega, from our definition of this Fourier transform for A, this time for vector potential. You see that this is related to a picture of radiation field in terms of photons. So think about this, how these related, this Einstein relation for photon energy, this is related to simple harmonic oscillator's energy, and how the similarity allows us to define a quantum field. But remember that all the treatment we have for these fields, basically a definition, but a definition which works, and in the future lectures we're gonna develop quantum field theory along these lines, and then we're gonna pass to path integral formulation. There you don't need this kind of formalism, but this is the beginning of canonical formulation of quantum field theory. You have to understand both ways, canonical and path integral methods. And after some, couple of steps, getting some understanding canonical formalism, we're going to move to path integral formalism. But that's it for now.